Good morning to all. Welcome to the 14th lecture. Today we are going to look at the maximum subarray problem. So towards the end of yesterday's lecture, we started defining the problem and arriving at a solution. So today we are going to discuss a divide and conquer solution. And we'll summarize the divide and conquer strategy for developing algorithms. Okay. Yeah, if possible, we'll give a brief introduction to greedy algorithms. Okay. So let's quickly start with the definition of the problem. So yeah, we'll go over it once again. We defined it yesterday. So suppose we are given daily stock prices of a company, so yeah, some target company over a certain period. Okay, maybe 30 days or 50 days or whatever, some n number of days, let's say. What we need to do is, so suppose we are going to buy and sell the stock in that period. Okay, but we haven't decided which day. So you can just imagine when I say period, certain number of days. So but we haven't decided which day should we buy and which day should we sell. Okay, now the idea here is, I mean the requirement here is compute the largest possible profit per share if one is to buy and sell the stock in that period. Okay, that is, you want to come up with the days I and j such that I is less than j, and the difference between the share prices during those days is a maximum. Okay, so should be a positive value. Let's take this example. So here is an array of 15 elements. Okay, you can just imagine this is a share price on day 1, share price on day 2, day 3, day 4, etc., etc. This is a 15th day. Now yeah, so let's take example. So if one is to buy on day 1 and sell on say day 4, okay, so then we'll make a profit of 6 rupees per share. Similarly, one is to buy on day 1 and sell on day 5, there is no profit, no loss. But if one were to buy on day 1 and sell on day 6, there will be a rupees 2 loss per share. Okay, so our goal is to find I and j such that the difference aj minus ai is maximum. So in this example, you can see that if you buy on day 3 and sell on, I think, day 12, this is day 12, right? Yeah, day 12, the profit is the maximum. So looking at this example, you will be tempted to think, okay, so isn't the solution very simple? Why can't I just get the minimum share price, the day on which the share price is minimum and the day on which share price is maximum? So in this example, it works so. Okay, so in this example, it just happened to be so. What we need is, so we need the minimum should also be less than, that is the day on which the stock price was minimum should also be less than the day on which the stock price was maximum, which need not be the case always, right? Yeah, so this constraint I less than j is what makes the problem complicated. So coincidentally, it so happened that for this example, it just works. If you take the minimum and maximum, it just works. It need not be the case. Okay, so minimum could as well have been here 11, let's say, and here it was, let's say, 13. Okay, so then our solution would have been 12 and 28. Okay, so instead of 11 and 28, so that is buy on day 2 and sell on day 15. So still you have maximum here, but yeah, but not minimum. So similarly, you can also, I mean, I could have swapped 28, I could have put 28 here, and then the solution would have been to pick 13, so 12 and 26. Okay, so it's not exactly minimum maximum. There is much more to it. Okay, so more formally, so we can assume that the stock prices are always given in an array. Okay, array of n elements. Our job is to compute I pairs I less than j, so I and j ranging from 1 to n, such that aj minus ai is the maximum. Okay, so the naive approach is to run over all such pairs. How many such pairs? I less than j. There are exactly n choose too many such pairs. Okay, so you run over all such pairs and compute aj minus ai. That takes into one arithmetic operation, which is subtraction, and then compute the maximum. So you'll require comparative number of comparisons, right? N choose to minus 1 many comparisons. Okay, so the overall time complexity will say order of n square. That is, n choose to is order of n square. Okay, so the brute force algorithm runs in quadratic time, that is order of n square time. The natural question is there a faster solution? We are going to see n log n time divide and conquer solution, and of course it should be noted that there are much better algorithms. Okay, there are linear time algorithms which we will not be seeing in today's lecture. Maybe while we discuss dynamic programming, we might look at the solution. But right now, our focus is to just to demonstrate that divide and conquer gives a better solution than the brute force. Okay, it also is a bit non-trivial to come up with. It requires a reformulation, like we saw in the last lecture. I'll go over it once again. Okay. Any questions so far? So we'll start with the reformulation. So let's take a slightly different view. So let's start with constructing a new array. Okay. Let me pictorially demonstrate how it looks like. So I have A of n elements. I'm going to construct a new array of n minus 1 elements. This is my B. 1 to n minus 1. Okay. Now, how are the elements? So it's basically the successive differences are what's stored in this new array. Okay. So new array B such that the ith element in this array is the difference between I plus 1th element in array A and ith element. That is in fact ai plus 1 minus ai. Okay, or in other words, you just subtract these two and put it here. Okay, subtract these two and put it here. Subtract these two and put it here, and so on. Okay, so there are exactly n minus 1 elements in this new array. So let's take a look at the example. Okay, so let's take our example array of 15 elements. Now, so the first element is minus 4, which is 12 minus 16. Next element is minus 1, which is 11 minus 12, and so on. So the last element is 27 minus 25. It should be plus 2. Okay. So the only thing is, well, see, when we talk about stock prices, right? Usually we don't talk about negative prices. So stock prices are always positive. Of course, there are exceptional circumstances where the stock price can go negative also. But yeah, in usual circumstances, it is never negative. Okay. So, but however, this array B has negative values too. Okay. That is particularly when the price drops immediately next day, then the value will be negative. Say 22 to 16, there was a drop. Okay. Yeah, so now let's just have a close look at what is happening. Okay, so let's say I'm just looking at this array. These values basically represent differentials, right? So it's easy to understand this by plotting a graph. Okay, so let's say 1, 2, 3, 4, etc., etc., etc. Now let's plot the values. Okay, so we are going to plot, so indices sum. Okay, so what we do is, so let us take so -4 here, so it was -4 here, -4. Okay, so initially it was -4, and then -4 plus -1, which is -5. Okay, and then plus 11, then this goes up. Okay, so 11 plus -5, which is 6. Okay, 6, it goes up like this, and then -6, which becomes 0, right? 0, and so on, then -2, then +5, and so on. Okay, so if you plot these summations, what do they represent? So let's say I'm looking at index I, so index 3, and index, let's say this is 4, 5, 6, 7. Okay, so if I sum the elements here, what do they represent? Or starting from the first, so that is what this plot represents, right? So this plot represents the cumulative values. Okay, but now how do I get the sum from the plot? I just subtract the value up to index position 4 from the value from up to index position 7. So that is, you look at the plot, you look at position 7, what was the value? Say this is 7, and then look at 3, what was the value? So 3 was here. You subtract the two values. That gives you the summation. Okay, so the graphical representation basically allows you to get the summation, one thing. And sorry, but what does it represent? Let's just have a look at it. Okay, so let's say I'm looking at, so I'm going to define a new quantity. So Sij is defined as, okay, so whenever I write equality with a triangle, that means I'm going to define. Okay, so this is defined as bi plus bi plus 1 plus etc plus bj. So let's write it in terms of a. What is this? What is this? So ai plus 1 minus ai plus ai plus 2 minus ai plus 1 plus etc 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 a j plus 1 minus aj. So now there is a telescoping that is happening. So ai plus 1 gets cancelled. Similarly, ai plus 2 gets cancelled, and so on. So what are the elements that are surviving? aj plus 1 and ai. So this is equal to aj plus 1 minus ai. That is the profit we can make by buying on day I and selling on day j plus 1. Okay. And these are the quantities that we were interested in, right? So let's go 2 slides back and see what was our solution. So we wanted I less than j such that aj minus ai is the maximum. Or in other words, we want I less than or equal to j such that aj plus 1 minus ai is the maximum, right? They are equivalent. See, I mean, only because of indexing, I have this aj plus 1 minus ai. Okay, so if I had started with indexing of b with 0, things would have been easier. But anyway, let's not worry about it. So I hope I'm making it clear, right? So what is the reformulation now? Somebody quickly.
Maximizing the difference between I less than j pairs is equivalent to finding the maximum sum in this array.
Yeah, so maximum sum of subarrays, right? Sum among the subarrays. So, or in other words, finding I less than or equal to j such that Sij is a maximum. Okay. So only thing is I need to put less than or equal to because of this j plus 1 here. Okay, I hope it is clear, right? Because when I equal to j, say S11, S11 basically A2 minus A1, right? So yeah, so let's just state it. So now the problem is equivalent to computing I less than equal to j. Okay, sorry for the error. So computing I less than or equal to j such that Sij is the maximum. Okay, so this is the maximum subarray problem. So this is maximum sum subarray problem. Yeah.
Hello, sir.
Yes. Yes.
So, sir, I have a doubt that
Yeah.
initially we were doing only one operation, that is subtraction, and now we are
Mhm.
doing multiple operations. So, miss, how it will be useful, miss?
Yeah, that's a very good
Because
point. I mean, when you say multiple operation, we are only doing addition, right? We're not
yes,
doing
yes,
anything else. I mean, we just needed to, I mean, subtraction and addition are equal in complexity, right? Yeah, but what you meant was for an I, so what you meant was for in the earlier version, for
yes,
ij, all you needed to check was ai minus ai, whereas sij, you need to sum,
yeah,
but many sums, I mean, many sum with many summands, right? Yeah,
yes,
that's a very
yes.
valid point. You're right. Okay. So, yeah, so let's just look at the brute force solution. So, what is the brute force solution once again? Brute force or
Miss,
naive solution.
directly differencing between each and every element, finding the difference.
Yeah, no, that was our earlier solution with this
Yeah.
reformulation. Let's imagine that we are just given B now instead of A. Okay.
Okay.
So in that case, what should it be? So you just for every I less than or equal to J,
Yes.
compute
Yes. Yeah.
Sij
Hmm.
and output the maximum.
Yes.
Okay. So total n minus 1 square pairs. Because I less than or equal to j, right? N minus 1 square by 2, I believe. Yes. Okay, I less than or equal to j. So n minus 1 square by 2 pairs. And for each pair, compute Sij. So this is order of n operations again, at most, right? Some cases it will be really small, some cases it will be large. So if you have a naive implementation of this idea, you'll require order of n cube.
Yes, sir.
Okay. But however, with the careful implementation, okay, so I'm not going to discuss it. So remember that you need to compute the summation for every pair I less than or equal to j, right?
Yes, sir.
So what you can do is you can actually do it in overall order of n square time. Okay, so together all of this can be done in order of n square time, but I'm leaving it as an exercise. Okay, so there is an algorithm that computes Sij for every I less than j in a total of order of n square time.
So, sir, is it like this that we want to compute means continuous values in an algorithm? So we are using this approach.
No, this approach because we'll get a better solution soon. Okay, so we'll come up with a better solution. Yeah.
Okay.
So I wanted to make a statement. So yeah, thank you. This approach right now. So you want to get the naive, match with the naive algorithm in the original problem, right? It was non-trivial. Okay, so I left it as an exercise. Okay, so the naive implementation of the brute force algorithm would take order of n cube time, but still it is possible to implement it in order of n square time. Okay, but then that is complicating the matters, right? So this reformulation only complicated the matter to even to get an order of n square time algorithm. Okay, but however, we'll see that with the divide and conquer view, we are going to get much better solution, and in fact a simpler solution too, though recursive. Okay, which is usually the case with the divide and conquer. Okay, so the interesting fact is divide and conquer view is a naive one. Okay, so there is not much.
Excuse me, sir. Hello.
Yes. Yeah.
Can you go back to the previous slide?
Yes. One slide previous or this one?
And one more previous where we have written something at the bottom.
Yeah.
Okay. So why did we write an equal to sign? Just it is less than, right?
No, that is because of this ai plus. See, that's because I'll be comparing j plus 1 with ji, right?
Okay. Because of that formulation.
Exactly.
Okay.
So I will have to, because I will be missing out on I and I plus 1. Okay. Otherwise.
Okay.
Yeah.
Thank you.
Yeah. Okay. So the divide and conquer view is fairly straightforward, though implementation of it will require a bit of, bit more observations. Okay, so the idea is fairly simple. So let's just split the array into two parts. So this is our array B. We have forgotten about A now. Okay, so let's say B is of length n. Instead of using n minus 1, I'll just use n. I hope people are comfortable with it. Okay, so now in this example, here n is 14. Okay, so our idea is to compute I less than or equal to j such that Sij is the maximum, right? Let's suppose we divide the array into two parts. The first part, let's call it as B1, and the second part we call it as B2. Okay. So in this example here, so I take B1 as up to -1, this portion, the first 7 elements, and the remaining 7 elements are B2. Okay. Now let's just look at the values Sij, that is subarrays. So now the subarrays can be categorized into 3, right? One is completely within B1, that is the starting index and the ending index are within B1. So if you take this example, those are indices S1 values S11, S12, etc., S67. Okay, I'm assuming 7 is the last index here. And there are subarrays which fall completely within B2. Okay. And then there are arrays which split across. That is I within this range, I is less than or equal to n by 2 and j greater than n by 2. Okay, or greater than or equal to n by 2. So yeah, so let's just think. So divide and conquer means you just subdivide or divide the instances and solve them independently and then somehow merge them, right? Or combine them into a solution. Okay. So now if I were to design a recursive algorithm, how would I do it? So I have 2 arrays in hand, right? So I recursively compute all Sijs, in fact, the maximum among all Sijs which is within B1. Similarly, all Sijs which is within B2 with the 2 recursive calls. Does that make sense? I'll write it precisely later, but I'm only describing it intuitively right now. Okay. Now, what is remaining is, so a recursive call will sort it out among all Sijs, which is, that is all subarrays which is within B1. Similarly, another recursive call will sort out all subarrays which is within B2. Okay. I mean, by induction again, because the array size drops by 2, a factor of 2. Now, only thing that I need to figure out is how do I deal with subarrays which are across. Can I make a recursive call for that? So just for simplicity, just for counting sake, so we have how many pairs that we require? Roughly n minus 1 square by 2, right? So n minus 1 square by 2 total pairs, okay? N square by 2, okay? So I'll just write it as n choose 2, okay? Okay, leave it, it's fine. This is an upper bound, okay? N square by 2. Sorry, n square by 2. Out of which, how many pairs fall completely within B1? Can somebody tell me?
N square by 4.
Yeah, so it is n by 2 square, right? And how many fall within B2? The same number, right? N square by 4. Okay. So, but there are still things which are left out, right? So what are the things which are left out again? Which is again the same quantity, n square by 4 or n by 2 whole square. Okay, so then my count of n by 2, n square by 2 is incorrect. So it should be n, let's take it as n square, okay? Because I said I less than or equal to j, right? So how much is it? If I less than or equal to j? N choose 2 plus n, right? What is n choose 2 plus n? So n into n minus 1 by 2 plus n. What is this? N square by 2. So it's n into n plus 1 by 2. Is that right? Yeah. So this is not exactly n square by 2 because otherwise it would have been cheating because we already have the count here. So it is n into n plus 1 by 2. Yeah, sorry, it's not n square by 2. Okay. So I still have a significant number of pairs which are left out, right? Which is basically those that start in the left array and end at the right array. Okay. So can I do a brute force solution for them? How many of them will there be? Quickly, somebody. So you choose an I from here and J from here. How many choices for I?
n by 2 for both.
N by 2 for both. So it's still quadratic, right? Yeah. So even after divide and conquer, so divide and conquer for this alone. So this subarray, let's write it as T of whatever, T of n by 2. This is T of n by 2. Sorry. Yeah. T of n by 2. But I still have a lot of work to do, right? Still n square by 4. Many pairs have to be computed. But then again, it's non-trivial, right? You'll have to sum and so on. So still there is some amount of brute force that is left out. Okay. Yeah. So that is where it helps to have a closer look at what these values represent. Okay. So let's just have a closer look at it. So I'll just redraw the array here again. Is it clear the idea that we are going to implement to everybody?
Sir, can you back to the one previous slide? I'm just
Yes.
confused with the part where these are the sums within B. So are we working with B or are we working with the array Sij? Is there an array of Sij which stores all these values?
No. So we are not storing the values. So we need to compute all of them, right? Eventually.
Yes.
And take the maximum, right?
Yes.
So see, compute all the values implicitly. We need not compute them explicitly and store somewhere. So what I was going to say is, see, I want to have maximum. So let's write. So what I want is, I hope, is it okay if I write here? Okay. So what we want is I less than or equal to j such that Sij is maximum. In other words, you want to compute this max I less than or equal to j Sij, right? Now what we are going to do is we are splitting this into 3 sets. Okay. So 3 sets. Let's call this as set S1, S2, and S3. So S1 consists all pairs which are within B1. S2 consists of all pairs which are within B2. S3 are the pairs which are across. Now if I compute maximum of this, and maximum of this, and take their maximum, that gives me the value, right?
Yes.
That's exactly what we are doing now. Okay. But the
so
only complication,
the B1 should also contain 6, 6 and 7, 7 also.
What do you mean by 7, 7?
S6, 6, S7, 7. Shouldn't it contain that?
No, why 7, 7 you need? Yeah,
Because
S7, 7 will be there. Yeah. So S7, 7, you're right. Your S7, 7 will it contain? 7, 7 involves 8, right? Yeah, so this 7, 7 is
I think
problem. 7,
I'm
7
not
means,
understanding the notation here. Since you said
no,
Sij represents selling on the J plus 1th day and buying on ith day.
no, that is okay. So I mean, see, I've just reduced it to the maximum sum subarray, right? I'm only talking about subarrays now.
Okay.
So the subarrays, so what are the subarrays which non-trivial subarrays which are within this? That's exactly this, right? So you're only looking at the subarray, right? So this 7, 7 will not come here because it should be based on the information we have about this array alone, right? So the subarrays are exactly this. Okay, so what I mean is, for now, let's forget about our reformulation. So the problem that we have in hand is compute an index I less than j such that the subarray starting from index position I to index position j, the sum of these elements is the maximum. Okay.
Okay.
Sorry for the confusion. Okay, sorry for the confusion. Okay, so for everybody else, so the problem that we are considering now is the maximum sum subarray problem. Okay, that is, we want to compute index ij such that sum from location I to location j is the maximum. For that, we can even have I less than j. We don't need I less than or equal to j. For our reformulation, we did need that, but it's not required anymore. Okay, it just can be taken care of by re-indexing. So yeah, so now is it clear, this split? So these are all subarrays which are within B1, all subarrays within B2. These are subarrays which are split across, and we are considering this corresponding sums. Okay, and these are the values that we are looking at. Okay.
Yes, sir.
Okay, so let's just quickly look at. Okay. So let's forget about the portions which are completely within B1, subarrays, and subarrays which are completely within B2. Okay. Now only interest is in subarrays which are across. Okay, sorry. Let's use this. Yeah. Let's say I have a subarray. Let's say I have a subarray which splits across. So I want to compute max sums of subarrays, all such subarrays. Okay. So how many possible subarrays? N by 2 into n by 2, right? As some of you pointed out. So I want to maximize this value, but let's just have a closer look at it. So if you consider any such subarray, right, you can split it into two subarrays. The slanted bars corresponding to the portion which is completely within B1, and the vertical bars is completely within B2. Okay. So for any such ij, that is subarray which starts in B1 and ends in B2, you can split it into two subarrays. One is completely within B1. Where does it end? It ends at position n by 2. And the other one is completely in B2. Where does it end? Where does it start? It starts at position n by 2 plus 1. Right? So this is true for any such subarray, right? Any subarray which spans across B1 and B2, you can split it into two portions. One portion lies completely within B1, the other portion lies completely within B2. Now our job is to compute maximum, subarray which maximizes a sum. How do you do that? Can anybody suggest an idea?
Maximum of all arrays from the left which end at n by 2 and from the right which start at n by 2 plus 1.
Very good. So we basically see if you take maximum among all possible and maximum among all possible here and add them, that should give you the maximum, right? See what are the possible arrays? So possible arrays here in B1, the interesting ones are basically 1 n by 2, 1 n by 2, 2 n by 2, 3 n by 2, etc., etc. Okay, that is S1. I'm sorry. S1 n by 2, S2 n by 2, S3 n by 2, etc., etc. S n by 2 minus 1 n by 2. And in the right hand side, it is n by 2 plus 1 comma n by 2 plus 2, n by 2 plus 2 comma n by 2 plus 1 comma n by 2 plus 3, and so on. So what are the corresponding sums are indicated? N by 2 plus 1 comma n by 2 plus 2, S n by 2 plus 1 comma n by 2 plus 3 and so on. Okay, S n by 2 plus 1 comma n. Now if you take maximum among these, max and maximum among these, and you sum, this is the max among Sij, I less than or equal to n by 2, j greater than n by 2. Do you all agree? See, what are our candidate sums? Basically pairwise sums, right? So you take one element from here and one element here, one element from here and one element from here, one element from here and one element from here. How many are there? N by 2 into n by 2. So n by 2 whole square many sums are there. But to compute the maximum, you can actually split them. You can do it independently, right? So I mean, intuitively, if I have two sets of values, okay, integer values, say a1 and a2. I'm sorry. Or A and B. Okay, A and B we have already used for arrays. Sorry. Say C1 and C2. So I want to, so this is set of elements, this is set of elements. So I want a pair from C1 and C2 such that way that their sum is the maximum. How do you do it? You take the maximum in C1 and maximum in C2 and add them. That's the only possibility, right? You cannot get anything better. Does it make sense? That's exactly what we are doing. Okay. So our thing was, we are basically looking for pairs or looking for arrays which start in B1 and end in B2 and take the maximum sum among them. But the crucial observation is any such array split into two. Okay. So the first portion, I have the corresponding subarrays are exactly n by 2 many, and similarly in the right hand side there are exactly n by 2 many or n by 2 minus 1. Okay. And what I actually am looking for is the set which consists of pairwise sums. Okay, pairwise sums of this, and I want to have maximum. How do I get the maximum? I pick maximum from the left hand side and pick maximum from the right hand side, add them. That will give me the maximum. So let's go back here. Yeah, so let's take this example just to be concrete. Okay, so this is my portion. Can you tell me where should I stop? 3, 3, 6, 7, minus 1, right? Okay. So this is my B1, this is my B2. Okay. Now, so what are the subarrays that we are looking at? The subarrays that we are looking at is, one is the whole array, the other one is this subarray, 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 and this. And from here, what are we looking at? This subarray, this subarray, this subarray, this subarray. Okay. Now to maximize, so what we do is so our candidate arrays or the arrays that we need to look, subarrays that we need to look into are the ones which start at B1 and end at B2. How do you obtain? You pick one subarray from here and one subarray from here. Each such combination gives you a required subarray. Now to compute the maximum, all we do is we compute the maximum here. So what was the maximum here? Can somebody tell me? What is the maximum sum? When I say maximum sum ending at n by 2, what is that? So I think it is 11 minus 6 minus 2, 5 minus 1. What is that? Minus 9 plus 16. That is 7, right? 7, yeah. 7 here. And what is it here? Starting with this position. Starting at this position. 6 minus 6, 0. plus 2 plus 8. So that is 10. Everything else is negative, right? Okay. So 10, right? So 10 plus 7, which is 17, which also happens to be our maximum. Okay. Is the solution clear to everybody? So now we are ready to write the algorithm. Okay. So now what we are going to do is we are going to split the array into half, recursively compute the maximum subarray in the first half, recursively compute the maximum subarray in the second half, and also compute these maximum among subarrays in B1 that end at n by 2, and similarly maximum sum among subarrays in B2 which start at n by 2 plus 1, that is start at the first index of B1 B2, sorry, and take the maximum. That is it. Okay, so let's write down the algorithm. So max sum, I just write it as max sum. Okay, max sum array B, size of the array n. Okay, so returns I less than j such that Sij is maximum. This is our specification. Okay, so what is our step? First step, construct B1 and B2. And nothing to construct, you just split the array into 2. Okay, so compute, let's say, okay, I'll use a different color. Okay, let's say I1 J1, which is by a recursive call with subarray B1. What is the size? N by 2. Again, as usual, I just ignore when the cases when n is odd. In that case, I'll have to have ceil or floor. Okay, in one case ceil and one case floor. So third step, compute I to J2, which is outcome of recursive call with array B2. Again, size is n by 2. Okay, so we'll just assume that we are copying into new array, so we don't worry about indices. Okay, and we need to compute other quantities for so let us say I3 be such that S I3 n by 2 is the maximum among S1 n by 2, etc., etc., S n by 2 minus 1 n by 2. Similarly, J3 be such that S n by 2 plus 1 J3. I hope I'm making sense. I'm using lots of sub indices, so I1, I2, I2, J2, and so on, is the maximum among S n by 2 plus 1, n by 2 plus 2, comma S n by 2 plus 1, n by 2 plus 3, etc., etc., S n by 2 plus 1 n. Okay, then so what is the last step? Can somebody tell me quickly?
Maximum in these three pairs.
Yeah, so you just consider, so output Ij such that Sij is max among Si1 J1, Si2 J2, Si3 J3. Okay, that is all. Okay, so this is the implementation of the idea. So that is a recursive call here, and this portion. So how do you implement this? So let's analyze the complexity here. Okay. So let's say Tn is our running time of our algorithm. Okay. Sorry. When I say running time, the number of operations, which could be arithmetic as well as comparisons. Okay. So what is the running time here for this recursive call?
T of n by 2.
T of n by 2. And for this recursive call, T of n by 2. Right? And how much work you need to do to compute these values, maximum among these?
Order of n.
Okay. How much work do you need to do? Let's just
Order of
quickly look
n.
at it. Order of n, good. So how do you do that?
We can
So I just start
find
from the midpoint. Yeah. Yes. Go ahead.
so sir, in the left subarray we can just go from midpoint up to 1 and find the maximum. And at P2 also we can go from n by 2 plus 1 to n and find the maximum, and then just add them in constant time. So we have covered n distance to order of n.
Yes, very good. So all we do is you just start from here, okay, successively compute the sums and keep track of the maximum. So first now this element alone, next add this to it and see which is the maximum, keep the maximum. You remember which index was the maximizing, and then again add this to the sum value and see if it is bigger than maximum, then keep this as maximum and note this index and keep on doing that. So one scan from right to left of this subarray immediately gives you the required value from the left hand side. Similarly, one scan left to right of this subarray B2, this is B1, gives you the right hand side value. Okay, so this portion, so this one is, I'll write it as n by 2 time. Okay, in fact it is order of n because you have to sum order of n, and this is order of n because you have to sum and compare, right? So it's basically n operations. So order of n. Sorry. Okay. So what is the recurrence? Can we write down the recurrence? T of n is less than or equal to 2 T of n by 2 plus, so order of n, I'll write it as Cn. So this is order of n log n, Master's theorem. Or master theorem. Okay. So that is it. So that is the algorithm. The complexity analysis is fairly clear. So what I want you to do is formally write down the argument, correctness. Okay. So how do you prove correctness? So you simply apply induction hypothesis. Okay. So by induction hypothesis, these two recursive calls are going to return you the correct value. Okay. Now you need a third claim stating that if you take maximum among these three, that is going to be the maximum. For that, all you need to do is our algorithm so partitions this Sij into three sets. Okay, one set which lies completely within B1, the other set which lies completely within B2, and the third one is a set of all subarrays and their sums which span across B1 and B2. Okay, so for that we need this observation that we made here. So if you have two sets C1 and C2, and I want element from here and element from here so that the sum is maximized, all I need to do is split the maximum element from here and split the maximum element from here. That sum is going to be the maximum. So that is the third observation. Okay. Yeah. So these three observations, I mean, these two things, that is induction hypothesis and the observation that to compute the max of among pairwise sums, all you need to do is take max from the left hand side and take max from the right hand side. That immediately gives, their sum immediately gives me the maximum. Okay. So this is the observation. So combined with these two gives the correctness. I'll skip it for now in case if people find it difficult, so we can discuss it during the tutorial hours or discussion hours. Okay, so that part is skipped. It's fairly straightforward to argue. So I'll skip this portion. So for complete details, so what I have given is more intuitive picture of the algorithm. So there is a complete analysis of this algorithm in CLRS book. Okay. CLRS Introduction to Algorithms book. It runs into like 4 or 5 pages. Okay, there's a complete description of the algorithm with I think close to an implementation version, not a program but like a pseudocode, and there is also complete analysis of the correctness. Okay, so one more reading exercise I want you to do. This is not a part of syllabus, but I want you to all know is Strassen's matrix multiplication. I had mentioned this in probably the second lecture, but we didn't discuss it. Okay, so we are not going to discuss it. Well, describing it is not very tedious. It's fairly straightforward, but we will not understand much more. I mean, it will just look like at another divide and conquer solution. We'll not get much intuition into what is happening there. Okay. So for those who are interested in, I mean, you can just search for complexity of matrix multiplication. There is a deep theory behind Strassen's matrix multiplication algorithm, which is beyond our course. Okay, so which requires a lot of algebra to understand. So we'll skip that portion. In the next lecture, it's already time. What time is it? Oh, 59. Okay, my God. So next lecture, we'll start with the greedy strategy. Okay, Friday we'll have tutorial as usual. If there is something that you need to discuss, please drop me an email. Okay, so I can include that in the tutorial discussion. Okay, thank you all.